Alright, hey guys, my name is Brittany and welcome back to a new probability and statistics video. If you're new here on my channel, I am a teaching assistant at the Georgia Institute of Technology for their industrial engineering department. I teach a mathematics course on probability and statistics, and I just run this small YouTube channel on the side just because I honestly love math and I love stats. Alright, so today we're going to talk all about geometric distributions, so let's get started. So when we're talking about geometric random variables and their probability distributions, we can describe them as discrete. And geometric probability distributions are defined by a random experiment. And this random experiment comprises Bernoulli trials. Bernoulli trials comprise only two possible outcomes. Can either be a success or a failure. And since these trials only comprise these two outcomes, they're inherently complements of each other. So the complement of a success is a failure, for example. We can also say that these trials are independent. So specifically in a geometric distribution, we're going to have some random number of trials and a fixed known number of successes, in which this fixed known number of successes is exactly one success. So we want to find the probability that our first success will occur on the nth number trial. And we'll ask ourselves, so what's the probability that the first time that we have a success trial is on the nth number trial? And since we're talking about the probability of our first success on the nth trial, this naturally presumes that all other trials prior to our first success trial are naturally failures. So for example, if we have some n number of trials, 1, 2, 3, 4, 5, so on, until our nth trial. And on our nth trial, we're going to get our first success. Let's just denote this as the letter X for now. That means that all trials before must be failures if our first success occurs on the nth trial. So all these before will be the complement of success. In other words, they'll be our failure trials. So expanding this concept, we can write a probability mass function for this discrete random variable. And we know that a PMF is represented by a little f of x function in which the probability of our random variable, in this case our geometric random variable x, is equal to some instance. And that'll be equal to the probability of success multiplied by the probability of failure, in other words 1 minus the probability of success, all raised to the power of x minus 1, where p is the probability of success and x is the number of trials. So we can actually break this down and explain why this really makes sense. So our first component is p, the probability of success. And so in a geometric distribution, we're only looking for our first success. So p represents our first and only success, which has probability of p. Now, 1 minus the probability of success is the probability of failure, in other words, the complement of success. And we're going to raise this to the power of x minus 1. In other words, the number of failures is equal to the number of trials, which is x, minus the number of successes, which is just one success. So x minus 1. We can also define the mean, which is represented by the Greek letter mu, which is equal to an e of x equation, which in this case for a geometric distribution is 1 over the probability of success. And our variance is just a sigma squared, which is equal to a v of x equation, which is equal to 1 minus p all over p squared. Alright, so this might seem just kind of like a bunch of random letters right now, so let's actually apply this in a real world example. So let's say, for example, we're playing mini golf. And our rate for getting a hole-in-one is 3% or 0.03. So let's find the probability that it'll take us till our 6th try to get our first hole-in-one. So let's draw this out first. So we want to find the probability that it'll take us our 6th try. So 1, 2, 3, 4, 5, 6 tries. And on our 6th try, we'll have our first hole-in-one. In other words, our first success. And we'll just represent this by the letter x. Now, if this is true, that means all these trials before must be failure trials. And the probability of a failure occurring is just 1 minus the probability of success, in other words, the complement of success, which is 0.97. And let's also note that our probability of success on our 6th try is 3%, which we know from the problem statement. And in this case, we're going to have 5 failure trials. And if we just combine these two, knowing our equation that we stated earlier, and the information about the number of failures and successes for this specific problem, we can multiply the two, saying that the probability of failure, which is 0.97, raised to the number of failures, which is 5, multiplied by the probability of one success, which is 0.03, is our solution for this problem. Now let's also find the mean. That'll be mu, which is equal to an e of x equation, and that's equal to 1 over p, which you can work out. You'll just get 100 over 3. So in other words, it'll take us about 100 over 3, which is approximately 33 tries on average until we get our first hole-in-one. And we can also find our variance, which is sigma squared, which is equal to a v of x equation, which is, as we defined earlier, our equation for variance. Just plug that in. We'll get 0.97 over 0.03 squared. All right, and that's pretty much all for today. I hope you were able to learn something new about geometric distributions, and if you've got any questions, just leave them down in the comments below and I'll be sure to get back to you. Thank you so much for tuning in, and I'll see you next time. Bye!